And 8 by 6 is 48, mod 10 is also 8. Ooh. Okay, so for that particular case, they are associative. Now, trust me, you could do this for all possible cases, all possible triples, and you'll find that this table is, with this binary operator, it is associative, right, of this form. So it takes this form for all ABC belonging to your set here, S, right, which is set 2, 4, 6, 8. Okay, so it's associative. Right, maybe now is a good time to start talking about this other set and see if we get something similar to this occurring here. And of course we do, because otherwise why would I be talking about it? Psychology of the teacher. Okay, so what is this set? Well, they're not integers as here. They are so-called symops, or symmetry operations. And what does that mean? Well, for example, take this equilateral triangle. In other words, the three sides are equal length. That's important. And this is the centroid of the triangle. And relative to this centroid, we can rotate this triangle. Let's say we rotate it anti-clockwise. So if I rotate that triangle about that point, about this centroid, if I rotate it by 120 degrees anti-clockwise, this C, this point here, will have moved to A, and A will have moved to B, and B will have moved to C. But as you look at it, so you're looking at it from here, it still looks like the same triangle in the same position, right? So that's why that operation of rotating it anti-clockwise for 120 is called a symmetry operation. Okay, so label that operation just R. Okay? So R, by definition, is a rotation anti-clockwise about the centroid by 120 degrees. That's R. Okay. Now S is another symmetry operation. So instead of rotating by 120, you rotate by 240, like double the angle. So you'll start here, and so there's 120, but you keep going, and you end up here, right, at 240. So to find that symmetry operation, that rotation, call it S. Okay. And this I here is just do nothing. Don't rotate at all. Okay. So you have here, in a sense, three, in a manner of speaking, you have here three rotation operations, and they all produce a symmetry. In other words, when you look at the triangle after the operation, after the rotation, it just looks the same. Right? So, okay. Well, there are three more symmetry operations. You're not rotating this time. You're well, you are in a sense. Or you could say like it's a mirror image reflection. Well, let's say it is a rotation, but you're rotating this way. Okay. So this point C would not change, but A and B swap, right? Because you're doing that. So and you call that operation Z, right? So that's the Z operation that way. And you similarly you've got one here. So if you rotate about that axis like that, call that Y, and you've got another one here. We call rotating sort of vertically like that. We call that X. So now you've got three more symmetry operations. So our set now, we have 6 for an equilateral triangle. We now have 6 symmetry operations, and we label them I, do nothing, rotate by 0 degrees. R, rotate 120 anti-clockwise. S, rotate 240. X, you rotate this way. Y, rotate that way. And Z, rotate that way. Okay? Alright, now let's assume, so that's the set. Now, what would be an interesting binary operation on that set? So if we take two of these symmetry operators, and what kind of binary operation could we perform on those two? Well, a really trivial one is just, so your binary operator is just simply followed by. In other words, you do one operation and it's followed by another one. That is as simple as that. You know, do this one first and then do that one. Now, so for example, say you perform the operation S first. So you're rotating it 240 degrees, and then, you know, followed by, then you perform operation X. So whatever this result was, you then do this, because that's what operation X is, right? You just reflect it about this axis. So whatever's here stays the same, but these two, whatever they are, swap. Okay? So you need to be careful about the convention, you know, the order, which comes first in a sense. Now you're doing S first, right? So S in a sense is closer to the triangle. So you perform S on the triangle, you do that first. And then you follow the result, you perform an X on it. Okay? Now if you do that, now imagine you cut out a piece of paper with an equilateral triangle, and on both sides of the paper, you in the corners, you know, you write A, B, C, and you turn it over and you write A, C, B, right? Now you can actually construct this binary operation table by doing all possibilities. So the form like Xi, Xj, where X is one of these 6. Okay, so you'll have 36 possibilities. It's actually constructing a binary operation table when the size of your set is n, integer n, then you will have n squared elements, wrong word, results, products. Your table will be of n squared size, and that can get fairly tedious. As n starts to climb, n squared gets very large, so a lot of work. So in this case, 36 cases, so I won't do them in real time, I've written them out beforehand. But watch. If you apply operation S, followed by operation X, the result, you know, the way the triangle looks and which letters are where, the result will be the same thing as if you applied operator Y to the triangle. You're going to have to trust me on that. If you don't believe me, it might be an interesting exercise for you. You cut out with a piece of paper or cardboard or something a triangle, and you know, write ABC in the corners, and then just construct this binary operation table. So S followed by X gives you the same result as if you just did one operation, which is Y. Now remember the convention on a binary operator table is you choose one of the column elements here, and that's what you do first, and then you choose one of the row elements here, and that's what you do second. So if we're doing S first, we're here, right? In the column. That's the convention. And then we do X. So it'd be SX. So SX here. We're there. Y. Okay? Alright. Now let's see if we can see. Now we know what this set is. So we've got these 6 symmetry operators, and we know what the binary operator is. It's just followed by. You do this operation first, and then do this other one second, right? Which one after the other, 2 of them. That's the binary operator, and you get this table. It takes a bit of work, but not too difficult. But if n gets large, like if n is 8, and then you've got 64 of these values to fill in, it gets really tedious. All right, but look, The same kind of pattern is happening here as happened here. For example, this unit idea. You know, there's one of the elements that when you use it, when you put it into a binary operation, the result is just what the other one was, what the other element is. Now if you do nothing, so